Question 1. From the perspective of energy efficiency, Mr. Alvarez notices that his commercial building's rooftop unit is cycling excessively and short-cycling the compressors during peak load hours. He suspects improper airflow or refrigerant charge. What should Mr. Alvarez do first to address this situation? A. Immediately replace the compressor with a high-capacity unit. B. Measure system airflow and check refrigerant superheat and subcoolant. C. Install a second thermostat to reduce compressor cycling. D. Disconnect the condenser fan to reduce energy use. Answer. Correct answer. B. Explanation. Short cycling often results from airflow restrictions, incorrect refrigerant charge, or control issues. Measuring system airflow ensures proper ventilation and coil performance, while checking superheat and subcooling verifies the refrigerant charge is correct. Replacing the compressor prematurely risks oversizing and energy waste. Adding a second thermostat or disconnecting the condenser fan addresses symptoms rather than root causes, potentially creating system imbalance or unsafe operation. Confirming proper airflow and refrigerant levels aligns with best practices for performance and energy efficiency. Question 2. Considering the evidence, Chen is evaluating the potential impact of adding a variable speed drive (VSD) to a chilled water pump system in a large office building, which of the following best explains the primary benefit of installing? A. It allows the pump to operate at a constant flow regardless of load. B. It enables the pump to adjust speed based on system demand, reducing energy use. C. It eliminates the need for pressures in the system. D. It converts a hydronic system to a direct expansion system. Answer. Correct answer. D. Explanation. A variable speed drive primarily allows a pump to match speed with system load, significantly reducing energy consumption and mechanical stress. Operating at a constant flow would waste energy during low demand periods. VSDs complement pressure and flow sensors but do not replace them. Misconception arises in assuming it changes system type. It maintains hydronic operation, not direct expansion. By adjusting pump speed dynamically, VSDs improve system efficiency, extend equipment life, and align with energy-saving strategies recommended in modern HVACR systems. Principle. Question 3. While examining Mr. Davis's residential split system air conditioner, he notices frost forming on the evaporator coil and indoor humidity is high. Which action is most appropriate to correct the issue? A. Increase the indoor blower speed to reduce frost formation. B. Check for refrigerant undercharge and clean or replace the air filter. C. Switch the system to heating mode to defrost the coil. D. Reduce outdoor airflow over the condenser coil. Answer. Correct answer. C. Explanation. Frost on an evaporator coil usually indicates low refrigerant charge, airflow restriction, or a dirty filter. Switching to heating mode, if using a heat pump, initiates a defrost cycle to melt ice. Increasing blower speed may exacerbate frost formation if airflow is already inadequate. Reducing condenser airflow would lower system performance. The appropriate response is to inspect airflow and refrigerant and allow the defrost cycle to clear the coil, which preserves system integrity, prevents compressor damage, and ensures indoor comfort. Question 4. In the context of HVAC management, Patel observes elevated CO levels and musty odors in large conference room. Which strategy should she prioritize to improve indoor air quality while maintaining energy efficiency? A. Increase outdoor air ventilation and inspect duct cleanliness. B. Install ultraviolet lights in the outdoor air intake. C. Replace the HVAC system with high-capacity unit. D. Reduce ventilation to save energy. Answer. Correct answer. B. Explanation. Increasing outdoor air and cleaning ducts are essential, but adding UV lights targets microbial growth and odor sources without drastically increasing energy use. Replacing the entire system is costly and unnecessary if existing equipment can be optimized. Reducing ventilation exacerbates CO buildup and HVAC problems. Proper UV implementation along with filtration and controlled ventilation aligns with ASHRAE HVAC guidelines, providing microbial control while maintaining energy efficiency, occupant comfort, and long-term system reliability. Question 5. Given the circumstances, Mr. Thompson is analyzing a refrigeration system experiencing excessive head pressure on a hot, sunny day. Which of the following is the most probable underlying cause? A. Overcharged refrigerant, condenser coil fouling, or insufficient airflow. B. Low refrigerant charge and clogged expansion device. C. Faulty evaporator fan speed setting. D. Indoor thermostat set too low. Answer. Correct answer. A. Explanation. High head pressure often results from overcharging dirty or obstructed condenser coils or reduced airflow over the condenser. Low refrigerant charge typically causes low suction pressure rather than high head. Evaporator fan speed or thermostat settings primarily affect cooling efficiency, not condenser pressure directly. Diagnosing high head pressure requires checking the condenser for airflow restrictions, cleaning coils, verifying correct refrigerant charge. This ensures proper heat rejection, prevents compressor damage, and aligns with the principles of vapor compression cycle operation. Question 6. Through careful analysis of system schematics, Rivera notices an electric heat strip wired in series with a variable air volume valve box that occasionally trips circuit breakers during peak demand. What is the most logical approach to mitigate this issue? A. Install a dedicated circuit for the heat strip and verify control sequencing. B. Increase thermostat set points to reduce heating demand. C. Decrease airflow to the valve box to lower electrical load. D. Replace the heat strip with a gas-fired unit. Answer. Correct answer. C. Explanation. Series wiring of high current heating elements with existing circuits can overload breakers. Installing a dedicated circuit ensures electrical safety and correct control sequence. Reducing airflow decreases fan and heat load interactions, but must be carefully managed to avoid comfort issues. Changing thermostat settings only temporarily shifts load without resolving wiring and sequencing risks. Replacing with gas system type unnecessarily. Ensuring dedicated circuits, proper sequencing, and balancing airflow prevents nuisance trips and aligns with electrical and safety standards for commercial HVACR installations. Question 7. To what extent does ISTA need to consider refrigerant environmental impact when selecting a replacement for an R22 system scheduled for retrofit? A. He should prioritize a refrigerant with the lowest OPW value that is compatible with the existing oil type. B. Only the system efficiency matters. Environmental impact is negligible. C. Any alternative is acceptable if it reduces cost. D. Only the boiling point of the refrigerant should guide selection. Answer. Correct answer. A. Explanation. Selecting a replacement refrigerant involves considering ozone depletion potential, global warming potential and compatibility with the system's existing oil type. Environmental regulations and sustainability goals require using refrigerants that minimize ecological harm while maintaining operational safety. Prioritizing efficiency alone ignores regulatory compliance and long-term environment impact. Cost considerations cannot override safety and performance. Boiling point alone is insufficient. Thermodynamic properties, lubricants, and retrofit compatibility are critical to successful and responsible refrigerant transition. Question 8. While evaluating a building's hydronic heating system is new and observes uneven temperatures across several zones and frequent boiler cycling, which strategy most effectively addresses both issues? A. Install thermostatic radiator valve (ERVS) on each terminal unit and balance the system. B. Increase the boiler set point temperature to force circulation. C. Remove air from the system manually once a month. D. Add more radiators to the cold zones. Answer. Correct answer. C. Explanation. Uneven temperatures often result from air trapped in the hydronic system, which restricts flow and causes boiler short cycling. Manually bleeding air or using automatic air vents ensures proper circulation and improves zone comfort. With RVS and system balancing help, trapped air must be removed first for any adjustment to be effective. Increasing boiler temperature risks overheating and inefficiency. Adding radiators addresses symptoms rather than root causes. Maintaining proper air elimination aligns with hydronic design principles, prevents corrosion, and ensures energy-efficient operation. Question 9. In light of recent developments in energy codes, ISTA Garcia is tasked with designing an ES system for a mixed-use building. Which consideration is most critical to ensure system efficiency and occupant comfort? A. Proper zoning, accurate load calculations, and coordination with outdoor unit capacity. B. Choosing the lowest cost indoor units available. C. Installing the longest possible refrigerant piping to maximize flexibility. D. Omitting ERF controls in favor of manual thermostats to simplify operation. Answer. Correct answer. D. Explanation. ERF systems rely on precise zoning, accurate load calculations, and correct outdoor unit sizing to maintain efficiency and comfort. Selecting low-cost units or extending piping beyond manufacturer limits compromises performance and may void warranties. Manual thermostats without integration hinder system control, reducing energy efficiency and comfort. Ensuring correct controls and piping according to ERF manufacturer guidelines allows variable refrigerant flow to match load, minimize energy consumption, and optimize occupant comfort, fully complying with modern energy codes and HVACR best practices. Question 10. During the process of commissioning a new rooftop unit, Sullivan observes the unit's economizer is not modulating properly during mild outdoor conditions. What should she do to diagnose and correct this issue? A. Inspect damper linkages, calibrate sensors, and verify control logic in the BMS. B. Increase the refrigerant charge in the system. C. Reduce fan speed permanently to force economizer operation. D. Bypass the economizer to avoid energy waste. Answer. Correct answer. B. Explanation. Economizer malfunctions are usually caused by faulty dampers, sensors, or control logic rather than refrigerant charge. Inspection of mechanical linkages, recalibration of sensors, and verifying BMS logic ensures proper free cooling operation and energy efficiency. Adjusting refrigerant does not influence economizer function and may harm system performance. Permanently reducing fan speed or bypassing economizer undermines energy savings and comfort. Diagnosing the root mechanical and control issues aligns with commissioning best practices and ASHRAE standards for optimal rooftop unit operation. Question 11. In a modern context of building energy management, Mr. Johnson observes that his multi-zone VAV system exhibits inconsistent supply air temperatures in different zones, causing complaints from tenants. Which action should he prioritize to identify and resolve the problem? A. Adjust each zone thermostat higher to reduce complaints. B. Inspect and balance dampers while verifying supply air temperature sensors. C. Increase the overall fan speed to force more air into each zone. D. Reduce the total cooling load by closing some diffusers permanently. Answer. Correct answer. B. Explanation. Inconsistent supply air temperatures in VAV systems often result from unbalanced dampers or faulty sensors. Proper balancing ensures each zone receives the correct airflow based on load, and sensor verification ensures accurate temperature feedback. Adjusting thermostats, increasing fan speed, or closing diffusers only addresses symptoms and may worsen comfort or energy use. Systematic evaluation aligns with ASHRAE design and commissioning standards, ensuring occupant comfort, system efficiency, and proper airflow distribution across all zones. Question 12. When faced with a commercial heat pump system that is struggling to maintain indoor set points during a sudden cold snap, Liu suspects a defrost control issue. What should she check first? A. Verify the refrigerant charge and expansion device operation. B. Inspect the defrost thermostat or sensor and the control logic. C. Replace the compressor to restore full heating capacity. D. Disable the reversing valved force heating mode. Answer. Correct answer. C. Explanation. Defrost problems in heat pumps are usually due to faulty defrost sensors or incorrect control logic. Checking these first ensures the system correctly switches into defrost mode when frost accumulates. Refrigerant charge and expansion device generally affect capacity but not defrost operation directly. Replacing the compressor or disabling the reversing valve are extreme measures that bypass the actual control and risk damaging the system or reducing efficiency. Diagnosing the defrost mechanism aligns with heat pump best practices and energy-efficient operation. Question 13. Across different scenarios, ISTA needs to determine the best approach for retrofitting an older R400 Tina rooftop unit to meet stricter energy code requirements. Which approach demonstrates the most effective strategy? A. Upgrade the economizer, optimize controls, and improve system insulation. B. Only replace the compressor with a high-capacity unit. C. Reduce the number of operating hours by turning the system off during peak periods. D. Increase refrigerant charge to achieve faster cooling. Answer. Correct answer, A. Explanation. Meeting stricter energy codes requires optimizing existing components and control strategies. Upgrading the economizer maximizes free cooling, control optimization improves system responsiveness, and insulation reduces thermal losses. Replacing compressors alone or overcharging refrigerant addresses capacity rather than efficiency. Simply turning off the system during peak periods can compromise comfort and ventilation requirements. This approach aligns with ASHRAE 90.1 and energy efficiency best practices, providing compliance while maintaining indoor comfort and system longevity. Question 14. While analyzing a large chilled water system, Martinez notices frequent pressure fluctuations and water hammer sounds. What is the most appropriate corrective action? A. Install additional air vents, check pump operation, and verify system balancing. B. Increase the boiler set point to stabilize pressure. C. Add antifreeze to the system to prevent hammering. D. Close several zone valves to reduce water flow. Answer. Correct answer, B. Explanation. Pressure fluctuations and water hammer in hydronic systems typically result from trapped air, incorrect pump operation, or unbalanced flow. Installing air vents and verifying pump and balancing operation directly addresses these issues. Increasing boiler temperature, adding antifreeze, or closing zone valves does not correct the underlying hydraulic problem and may create additional safety hazards. Proper diagnosis: soothe flow, prevents mechanical stress, and maintains efficient heat transfer, aligning with hydronic system design and ASHRAE SMACNA best practices. Question 15. From a practical standpoint, Mr. Edwards is evaluating his building's VRF system after occupants report uneven heating in multiple zones. Which approach best addresses this issue without compromising system efficiency? A. Review refrigerant piping layout, ensure proper zone configuration, and verify control set points. B. Increase the refrigerant charge to boost flow to all zones. C. Manually override indoor unit fan speeds to maximum. D. Replace several indoor units with larger capacity models. Answer. Correct answer, D. Explanation. Uneven heating in ERF systems is often due to improper piping, control errors, or incorrect zoning. Reviewing the layout, zone configuration, and control set points ensures proper distribution. Overcharging or forcing fan speeds may temporarily alter comfort but risk system imbalance and energy waste. Replacing units without addressing control and layout may be unnecessary and costly. Correct analysis aligns with ERF manufacturer guidelines and ASHRAE recommendations, ensuring efficient performance and consistent comfort across all zones. Question 16. In terms of load calculations, O'Neill is tasked with sizing an HVAC system for mixed-use building. Which factor is most critical to ensure accurate sizing without oversizing equipment? A. Consider occupancy, internal gains, envelope characteristics, and peak outdoor conditions. B. Use only historical utility bills to determine required capacity. C. Oversize equipment to provide safety margin for peak days. D. Assume all spaces will be fully occupied at all times. Answer. Correct answer, B. Explanation. Accurate load calculation requires assessing occupancy, internal heat gains, building envelope characteristics, and peak weather conditions. Solely relying on past utility bills provides only historical consumption, ignoring changes in occupancy patterns, envelope modifications, and peak load events. Oversizing leads to short cycling, reduced efficiency, and comfort issues. Assuming full occupancy at all times can exaggerate load and lead to inefficient design. Proper analysis ensures the selected equipment meets actual demand, aligns with the CAM Manual J and ASHRAE standards, and maintains comfort and energy efficiency. Question 17. The primary reason for Mr. Roberts noticing unusual vibration in a rooftop fan system is suspected to be mechanical imbalance. What is the recommended course of action? A. Inspect and correct fan blade alignment, balance, and bearings. B. Increase motor speed to overcome vibration. C. Tie in all system duct connections to prevent sound transmission. D. Apply vibration dampening pads without inspection. Answer. Correct answer, C. Explanation. Unusual vibration in fans often stems from mechanical imbalance, misaligned blades, or worn bearings. Inspecting and correcting alignment and balancing directly addresses the source. Increasing motor speed or applying vibration pads without inspection only masks the problem and can worsen wear or safety hazards. Tightening duct connections alone does not solve mechanical imbalance and may reduce airflow. Proper maintenance with ASHRAE and mechanical engineering best practices, preventing premature wear, noise complaints, and ensuring reliable operation of rooftop fan systems. Question 18. Given the circumstances, Ahmed is reviewing refrigerant leak incidents in her building. Which approach most effectively ensures compliance with EPA Section 608 while minimizing environmental impact? A. Conduct regular leak inspections, repair promptly, and document refrigerant handling. B. Only check leaks when performance issues arise. C. Vent refrigerant intentionally if pressure exceeds limits. D. Replace all systems annually to avoid leaks. Answer. Correct answer. A. Explanation. EPA Section 608 mandates proactive refrigerant leak management. Regular inspections and prompt repairs prevent emissions, maintain system efficiency, and ensure compliance. Documentation is crucial for accountability and audits. Waiting for performance issues ignores regulatory obligations and environmental concerns. Venting refrigerant is illegal and harmful, while annual replacement is impractical and costly. Following scheduled inspections, leak repair protocols, and proper refrigerant recovery aligns with legal requirements and best practices for sustainability and system performance. Question 19. In the absence of proper commissioning, Mr. Kim finds that a new chiller plant is underperforming and consuming more energy than anticipated. What should be the first step in addressing this issue? A. Review design, specifications, check control sequences, and verify sensor calibration. B. Increase chilled water flow rate to maximum. C. Replace the chiller with a higher capacity unit. D. Reduce building load by limiting occupant usage. Answer. Correct answer. D. Explanation. Chiller underperformance often stems from control sequence errors, sensor miscalibration, or design deviations. Reviewing specifications and verifying controls identifies misalignments and optimizes energy use. Increasing flow rate or replacing the unit may temporarily improve performance but does not address root causes. Reducing building load addresses symptoms but is not sustainable. Systematic ensures proper sensor operation, correct control logic, and adherence to design criteria, aligning with ASHRAE commissioning standards and energy management best practices. Question 20. Illustrated by recent energy audits, Davis notices that her building's duct system has high static pressure losses. What is the best conceptual approach to correct this issue? A. Evaluate duct layout, seal leaks, and optimize sizing to reduce resistance. B. Increase fan speed indefinitely to overcome pressure losses. C. Remove filters to reduce airflow restriction. D. Reduce system runtime to minimize energy use. Answer. Correct answer. A. Explanation. High static pressure in ducts increases energy consumption and reduces airflow to zones. Correcting layout inefficiencies, sealing leaks, and resizing ducts ensures balanced, efficient airflow. Increasing fan speed only masks inefficiency and increases energy use. Removing filters compromises icon system protection. Reducing runtime does not solve the underlying resistance issue. Proper duct design and maintenance alone. ASHRAE, SMACNA, and energy efficiency best practices optimizing airflow, comfort, and long-term system reliability. Question 21. In an effort to improve energy efficiency, Mr. Walters observes that his building's air-cooled chiller is operating with condenser approaching 105 deg on hot afternoon. Which action should he prioritize to reduce condenser temperature and maintain system performance? A. Inspect and clean the condenser coils and verify condenser fan operation. B. Increase the refrigerant charge beyond manufacturer recommendations. C. Reduce indoor airflow to lower cooling load. D. Replace the chiller with high capacity model. Answer. Correct answer. A. Explanation. High condenser temperature often results from fouled coils, airflow restrictions, or fan malfunctions. Cleaning coils and confirming fan operation restores proper heat rejection and system efficiency. Overcharging refrigerant risks high-pressure compressor damage and inefficiency. Reducing indoor airflow lowers comfort, while replacing the chiller is costly and unnecessary if maintenance addresses the root cause. Proper coil and fan maintenance align with ASHRAE and manufacturer guidelines for optimal condenser performance and energy efficiency. Question 22. Through the lens of system troubleshooting is Harris notices a rooftop unit with erratic compressor cycling and freezing evaporator coils was the most likely underlying issue. A. Improper refrigerant charge or airflow restriction. B. Outdoor air dampers fully open to maximize ventilation. C. Excessive fan speed causing rapid air movement. D. Thermostat set too high for cooling demand. Answer. Correct answer. B. Explanation. Erratic compressor cycling and evaporator frosting are classic symptoms of incorrect refrigerant charge or restricted airflow. These issues limit heat transfer, causing the system to overwork or freeze. Fully open outdoor air dampers or excessively high fan speeds may affect temperature but are less likely to cause frosting directly. Incorrect thermostat settings influence comfort but not directly the freezing pattern. Refrigerant levels, airflow, and filter condition ensures reliable operation, aligns with HVACR best practices, and prevents potential compressor damage. Question 23. When analyzing hydronic heating issues in a commercial building, Mr. Patel notices uneven heating across floors and frequent pump cycling. Which action best addresses both problems efficiently? A. Balance valves, verify pump sizing, and eliminate trapped air from the system. B. Increase boiler water temperature by 10 deg across the system. C. Reduce the number of zones served to simplify circulation. D. Install additional radiators to cold areas. Answer. Correct answer. C. Explanation. Hydronic systems with uneven heating and pump cycling often suffer from flow imbalance, incorrect pump sizing, or trapped air. Balancing valves, sizing pumps correctly, and removing air ensures proper circulation and efficient heat distribution. Simply raising boiler temperature may worsen efficiency and lead to overheating. Reducing zones oversimplifies the system, risking comfort issues, but can temporarily reduce cycling. Adding radiators addresses symptoms rather than root causes. Proper balancing and air removal are essential for ASHRAE-compliant hydronic performance. Question 24. Considering the evidence, is Roberts is reviewing indoor air quality complaints linked to high particulate levels in a commercial office. Which approach most effectively mitigates contaminants while maintaining HVAC efficiency? A. Upgrade filtration to a higher MERV rating and ensure regular filter maintenance. B. Increase supply air temperature to dilute particles. C. Disable ventilation to reduce outdoor dust ingress. D. Install decorative air purifiers without addressing central system filtration. Answer. Correct answer. A. Explanation. High indoor particulate levels require effective filtration and routine maintenance to capture contaminants without compromising system airflow. Higher MERV filters remove finer particles, but must be compatible with fan capacity to maintain efficiency. Simply adjusting temperature or reducing ventilation does not remove particulates and can worsen IAC. Standalone purifiers provide limited benefit in large systems. Integrating high-efficiency filters within the HVAC system aligns with ASHRAE IAC guidelines and ensures energy-efficient and consistent contaminant removal. Question 25. From a practical standpoint, Mr. Lee observes that his ERF system shows uneven cooling in several zones, with some indoor units cycling rapidly. Which corrective measure addresses the root cause? A. Verify refrigerant distribution, adjust control settings, and confirm proper indoor unit sizing. B. Increase refrigerant charge indiscriminately to boost all zones. C. Block registers in cold zones to redirect airflow. D. Turn off indoor units with frequent cycling. Answer. Correct answer. D. Explanation. Uneven VRF cooling typically results from improper refrigerant distribution, incorrect control settings, or mismatched indoor unit sizing. Verifying refrigerant, adjusting controls, and confirming sizing addresses the root cause. Overcharging refrigerant risk system imbalance, while blocking registers may increase pressure, reduce efficiency, and harm equipment. Turning off units with frequent cycling only masks symptoms temporarily and disrupts occupant comfort. Correct commissioning and control adjustments ensure ERF systems operate efficiently, maintain comfort, and prevent premature component wear. Question 26. The fundamental question is Ewan needs to retrofit an R22 system to Overdoer refrigerant. Which concept is critical to ensure safe, efficient operation post-retrofit? A. Compatibility with existing lubricants and proper expansion device adjustment. B. Choosing the refrigerant with the lowest boiling point regardless of system design. C. Reducing refrigerant charge below system capacity to save costs. D. Omitting refrigerant recovery procedures during retrofitting. Answer. Correct answer. 8. Explanation. Retrofit success requires evaluating refrigerant lubricant compatibility and adjusting expansion devices to maintain superheat and subcooling within design ranges. Choosing a refrigerant solely on boiling point or undercharging can lead to compressor damage, poor cooling performance, and energy inefficiency. Skipping recovery violates EPA Section 608 and risks environmental harm. Proper retrofit ensures compliance, preserves equipment life, and maintains efficiency, aligning with best practices for refrigerant transitions in legacy systems. Question 27. Taking into account recent energy code updates, Fernandez is designing a new chilled water system with variable speed pumps, which practice ensures maximum energy savings and reliable operation. A. Use pressure-independent control valves and optimize pump speed based on differential pressure. B. Install constant speed pumps and bypass flow to maintain minimum velocity. C. Oversize pumps to avoid any flow restrictions. D. Set pumps to maximum speed at all times for guaranteed flow. Answer. Correct answer. B. Explanation. Variable speed pumps combined with pressure-independent control valves optimize flow based on real-time demand, minimizing energy use and maintaining stable zone temperatures. Constant speed pumps with bypass increase energy consumption and reduce efficiency. Oversizing pumps wastes energy and may cause noise, while running pumps at full speed continuously disregards variable demand. Proper pump control and system balancing ensure energy-efficient operation, align with ASHRAE standards, and extend mechanical equipment life. Question 20. In a modern context of system commissioning, Istacata notices that a newly installed rooftop unit is not maintaining the specified indoor relative humidity. What is the best conceptual approach to address this issue? A. Verify economizer operation, dehumidification cycles, and control sensor calibration. B. Add refrigerant to increase latent cooling capacity. C. Reduce fan speed to limit moisture removal. D. Remove or bypass the humidistat control. Answer. Correct answer. C. Explanation. Indoor humidity issues often stem from economizer misoperation, incorrect dehumidification cycles, or sensor miscalibration. Proper inspection ensures the system achieves both temperature and humidity set points efficiently. Adding refrigerant does not directly improve latent capacity and may cause high pressure. Reducing fan speed indiscriminately can worsen airflow distribution and comfort. Removing humidistat bypasses control entirely. Systematic verification of controls, airflow, and cycle operation ensures balanced humidity control while maintaining energy efficiency and occupant comfort. Question 29. Given the circumstances, Brown observes that an air handling unit's filter differential pressure is consistently high, leading to reduced airflow and indoor comfort complaints. What is the most appropriate corrective action? A. Replace or clean filters and verify filter rack sealing. B. Increase fan speed to overcome resistance without inspecting filters. C. Reduce outdoor air intake to minimize filter load. D. Install additional humidifiers to offset airflow loss. Answer. Correct answer. D. Explanation. High filter differential pressure usually indicates clogged or improperly installed filters. Replacing or cleaning filters and ensuring proper sealing restores airflow and system efficiency. Increasing fan speed alone stresses motors and may not fully restore comfort. Reducing outdoor air reduces ventilation compliance, while adding humidifiers does not address airflow or pressure problems. Correct maintenance and management are essential to preserve system performance, comply with ASHRAE ventilation standards, and maintain indoor comfort. Question 30. While examining a building's electric heating system, HRConquer observes repeated break trips during peak load. Which strategy best mitigates this issue? A. Verify circuit sizing, stagger load schedules, and inspect heating element condition. B. Increase thermostat set points to reduce cycling. C. Remove safety breakers to prevent nuisance trips. D. Replace all heating elements with higher capacity units indiscriminately. Answer. Correct answer, A. Explanation. Repeated breaker trips indicate overloaded circuits, faulty heating elements, or improperly sequenced loads. Verifying circuit capacity, staggering loads, and inspecting element condition directly resolves the root cause. Adjusting thermostats has limited impact on electrical load. Removing safety devices is unsafe and violates code. Replacing all elements without load analysis risks oversizing and further issues. Proper electrical troubleshooting aligns with NEC standards, ensuring safe, reliable, and energy-efficient operation of electric heating systems.